So I'm going to tell you a little bit today about studying the beginning of the universe from the bottom of the world, and how scientists like us go to the South Pole, in the most remote place on Earth, to learn about the origins of the universe, and also to study black holes, some of the most extreme objects in the universe. So from the point of view of a cosmologist, if you want to learn about the history of the universe, all you really need to do is look up, because doing astronomy and telescopes are like time machines. When we're looking at objects in the sky, the finite speed of light is causing us to look at the objects, see the objects as they were in the past. The sun is about 8 light minutes away, the nearest star is sort of a few light years away, and galaxies are sort of on the order of 10 to 100,000 light years across. So if we want to see the universe as it was in its past, we just have to observe the sky. So you might think that a good way to learn about the history of the universe would just to take the most powerful telescope we've ever built, the Hubble Space Telescope, point it at a patch of the sky and do an ultra-deep long exposure. And we've done that, so-called Hubble Deep Field, pictured here, where this is basically a patch of the sky equivalent to basically a pinprick in a piece of paper held at arm's length, so a very small patch of sky. But in that patch, with this sort of 3-month-long exposure that we've taken with the Hubble Space Telescope, we've discovered on order of 10,000 galaxies. It might be a surprise to you that most of these objects in this image are not stars, but they're distant galaxies billions of light years away. So from the point of view of an astrophysicist, you can learn, an astronomer, you really learn a lot about the universe this way by studying the most distant galaxies that we can find with an image like this. But from the point of view of a cosmologist who really wants to learn about the origin of the universe, the beginning of the universe, as far back as we can see, it's still a bit of a disappointment, because try as we might with this Hubble Space Telescope, still most of the space in between the galaxies is still all black. We haven't looked back to the very earliest instance in the universe. So it might be useful to also step back and sort of think about astronomers' view and about the origin of the universe. So in the 1920s, astronomers largely believed in a static universe. You'd look up at the night sky, you'd see the universe as largely homogeneous and unchanging, and this led to the theory of a static universe. So when Einstein wrote his theories of general relativity to explain gravity and tried to apply it to the universe on these large scales that we're observing, he basically fudged his equations when applied to the universe and included this thing called a cosmological constant to basically set it up such that the universe fit the static universe that astronomers at the day believed in. And later he would call this his greatest blunder, and I'll talk a lot more about that. So it's easy to forget the Big Bang. While the Big Bang theory is the predominant scientific theory to explain the origin of the universe, it's actually been around for a long time, and it sort of permeated popular culture, been mocked, to a certain degree. But remarkably, it's been around since 1927, and it was first proposed by this Belgian Catholic priest, Georges Lemaitre, who tried to apply Einstein's theory of gravity, theory of general relativity, to the universe, hypothesizing that the universe began as a primeval atom, as he described it, that began in this very hot, dense state, but then started expanding from this explosion at its very earliest instance. And so he theorized a universe that obeyed those laws of physics, applied Einstein's general relativity to it, and came up with what we now know as the Big Bang theory. And actually, shortly after, 6 years after, Einstein and Lemaitre went on a book tour together in California, pictured here on that book tour. And by that time, Einstein had already said, this is the most beautiful and satisfactory explanation of creation to which I've ever listened to. So even 6 years later, Einstein was a believer, and the Big Bang theory had become the predominant explanation for the origin of the universe. So what changed in that brief amount of time? And the first big piece of evidence that we had that a Big Bang happened was this discovery of an expanding universe. So when astronomers of the day started looking out at galaxies, collections of millions of stars, much like our Milky Way galaxy, they discovered that even back then, that the most distant galaxies, the further away a galaxy was, the faster it moved. And this so-called led to this so-called Hubble diagram, which basically is just a plot of the velocity, how fast the galaxy is moving away from us versus the distance. And this is showing a modern measurement of the Hubble diagram for some nearby supernova. So for hundreds of millions of light years away from us, we can tell that this Hubble law, this expansion, the further away something is, the faster it seems to be moving away from us. seems to be applied. So this has sort of led to this notion that the universe must be expanding, which fits well with the Big Bang. In addition, you can think about it in terms of trying to look back at this very earliest instance of the universe. So you can think of what would you see. And so from the perspective of looking up at the night sky and seeing the universe as it was in its past, when you're looking back, you're sort of, as you look back and further away, you're seeing the universe as it looked older in time, older and older galaxies, the first galaxies that formed the universe getting hotter and denser. And at a certain point, you'll reach this period in the universe's history where the universe was so hot and so dense that it was literally on fire. And you can sort of think of this sort of akin to when looking at the surface of the sun, for example. Like when we're looking at the sun, we're really seeing the surface of the sun, right? When the surface of the sun is about 6,000 degrees, it's a hot plasma. Electrons and protons have been ionized, turning hydrogen into this ionized hot, literally fire plasma gas. And basically you can't see through the surface of the sun. You can't see through that photosphere. You can't see through the center of the sun. And the same thing is basically true in this, looking back into the very early universe. At a certain point when we look far enough back, you run into this wall of fire, which is basically when the universe is about 4,000 degrees, when all the universe got completely ionized because it was so hot and dense, and we just can't see any further. But very quickly, as that universe continued to expand, the universe cooled, and around 400,000 years after the Big Bang, we expect the universe cooled enough that this hot plasma turned into neutral hydrogen. And if we look back far enough, we can sort of see that photosphere, much like we see the surface of the sun. We can look back to look at the photosphere of the universe when the entire universe was on fire. So, you might expect that would be pretty bright, even though it's so far away. And in 1965, Penzias and Wilson discovered what we now call the cosmic microwave background, which is this leftover light, the leftover heat from just after the Big Bang, from this period 400,000 years after the Big Bang, at this moment that the universe cooled so that neutral hydrogen could form. And even at the time, and later Penzias, Wilson, there's a famous story of them. They worked for Bell Labs. They were trying to calibrate their radio telescope, and they saw this glow wherever they looked on the sky when they were trying to calibrate the telescope, and they tried to understand what it was. They thought it might be bird droppings in the mirror, but eventually they just became convinced it was coming from the sky, and it was this bright object. And immediately at the time, it was recognized as smoking gun evidence for the Big Bang, and I'll talk about why we think that and know that. And then very soon after, won the Nobel Prize. And even at the day, as soon as they saw it, it all made the headline in the New York Times, May 1965, signals imply a Big Bang universe with the same telescope. So when I talk about microwaves, just so it's clear, I'm talking about microwaves are just light, right? So light can have different wavelengths. Visible wavelength is on the order of several hundred nanometers. X-rays and gamma rays have some of the shortest wavelengths, the highest energy photons, or light. And then towards the other end of the spectrum, with long wavelength light, you have radio waves, microwaves, infrared. So microwaves are basically something in between the wavelength of radio or infrared light, which has maybe a wavelength roughly on the scale of a honeybee. So maybe a few millimeters, half an inch kind of size nature. So it's pretty low energy light. But what's remarkable is if you took a census of all the energy in the universe in the form of photons or lights, what you discover is that the CMB, this light left over the Big Bang, is the brightest thing in the sky. So this is a plot of energy versus wavelength. So, optical is mainly stars, infrared are stars enshrouded in dust. But then if you look at this, the CMB, you'll see if you took a census of all the energy, the brightest thing in the sky is this cosmic microwave background. So over 90% of the energy in the form of photons even today, is still in the form of this light of the CMB. So it's literally brighter. This leftover light from the Big Bang is literally brighter, 10 times brighter than all the stars that have ever existed in the history of the universe. So it's the brightest thing in the sky. And it's one of the reasons we know it's due to this, and it sort of makes sense. It's from a period when the entire universe was literally on fire, and we're just seeing that light today. So how do we measure it? Well, you've all detected the CMB, or at least the older ones in the audience, with a TV antenna. Basically, about 1% of the static on your TV, just using a typical TV antenna, which sort of measures light at sort of hundreds of megahertz range, 1 gigahertz range, or tens of centimeter wavelength. About 1% of the static in your TV is due to the CMB, remarkably. So you don't actually have to try very hard to detect it. Even with a simple TV antenna on your house, it's so bright that you can actually just see it by accident. And that's why Penzias and Wilson found it accidentally. It was so bright they couldn't ignore it. So that's one remarkable fact about the CMB. It's the brightest thing in the sky, and that's one of the reasons we know it's from this early period in the universe. But in addition, the second remarkable fact about it is that it's extremely uniform. So it took almost 30 years until the COBE satellite to see any structure in the CMB at all. So this is a satellite, an image of it, or a cartoon of it, launched in 1992. They made this map that showed basically these are fluctuations or variations in the brightness of this microwave background to 1 part in 100,000. So even though it's so bright, it's uniform to 1 part in 100,000. So if you look 14 billion light years in that direction and 14 billion years in the opposite direction, that light from opposite ends of the universe is the same brightness to this 1 part in 100,000. It also measured that it was had this perfect black body spectrum, which I'm not going to talk much about, but also gave it, it's the most perfect, clean spectrum that we've ever measured in the universe. And this COBE measurement also led to Nobel Prizes for John Mather and George Smoot. So just to talk a little bit more about this map, just to make clear what we're seeing here. So this is an image of the whole sky in microwaves projected onto a 2D sphere. So similarly, you might project the entire globe, 3D sphere of the Earth, projected onto this sort of 2D image. And so if you sort of did the same thing for what Penzias and Wilson would have seen in 1965, it would look something like this, right? It just looked the same in every direction. As far as they could tell, it was just this uniform glow, lighting up the whole sky. That was the brightest thing they could see, but they couldn't see any variation in it at all. So it took 30 years to see this, just showing that structure, this 1 part in 100,000 variation in the brightness, or really the distribution of matter in the very early universe, only 400,000 years after the Big Bang. In a period, before there were stars, before there were galaxies, when this universe was literally this relatively homogeneous, uniform ball of gas. So what's so remarkable about this? Well, even at the time, Stephen Hawking, when shown the COBE result, talking about the COBE result, said that it was the discovery of the century, if not all time, right? So it's not, it's a pretty bold statement. But it's in some ways it's really is true. It's remarkable that because this is really a baby picture of the universe. Somehow we've been able to look back 14 billion years, only 400,000 years after the Big Bang, and make a baby picture, an image of the universe in such a drastically different state than the way the universe is today, and to try to help put that in better context and just sort of zoom in on some of these fluctuations. So these fluctuations that we're seeing, even though they're so faint. Given 14 billion years of time for gravity to start pulling in those slight overdensities, these are slight overdensities in matter in the very universe, just given time and gravity will start pulling that structure together, and those densities will grow and become more overdense. So this is showing a simulation of how this structure is varying on cosmological scales as we evolve time, and that structure grows and grows. And so this is just showing this colors are just showing the density of matter on these sort of billion light year, hundreds of million light year scales. And so, those slight overdensities in the very early universe are sort of seeding the structure at later times and seeding all the structure that we see in the universe. And that structure, is eventually going to seed all the galaxies that we see in the universe. And seed the Milky Way itself, our own galaxy, and eventually the Earth, right? So if you sort of think about it in terms of putting this on a sort of this universal cosmological scale onto sort of a person's scale in terms of time, people often call this the cosmic wave background an embryonic picture of the early universe, because if you put it on this sort of people equivalent lifetime scale, and say, the universe today with these galaxies, these clusters of galaxies, the structure we see around us, if you consider that a person near retirement, if you put that on a sort of equivalent time scale of this image that we're measuring with the microwave background, it'd be equivalent to something on the order of the first several minutes of a person's lifetime. So, to actually view the universe, today and then compare it to how it looked like 14 billion years ago, 400,000 years after the Big Bang, we're getting this incredibly long lever arm in terms of understanding the universe, the content of the universe, the evolution of the universe, and the laws of physics on these big cosmological scales to test our models of cosmology and physics. Okay, so a little bit of background. I'll talk a little bit. So how does this connect to the South Pole? So it turns out the South Pole is the best place in the world to do these observations of the light from the Big Bang, the CMB. So this is what the South Pole looks like. You're on about a 10,000 foot thick ice sheet. So the bedrock is sort of only about 200 feet above sea level, and there's a 2-mile thick sheet of ice on top of that. And so it looks pretty flat in every direction just because it is this ice sheet, this complete plateau of ice. And the South Pole Station can house about 150 people. We'll talk a little more about it, but it's basically right next to the geographic South Pole. And roughly a kilometer away from it is this so-called dark sector where all the astronomical experiments are at the South Pole, including my project, SPT, South Pole Telescope, which I'll talk more about. So what makes the South Pole in particularly unique to do these observations and the best place in the world is that it's extremely dry. So in the South Pole winter, temperatures can get down to minus 100 Fahrenheit. And when the air gets that cold, literally all the water vapor just freezes out of the atmosphere. And water vapor is really important for microwaves because water vapor absorbs microwaves. So literally, the South Pole is the driest place on Earth. If you compare it to the highest deserts in Chile, other mountaintops, Mauna Kea in Hawaii, it's factors of several less precipitable water vapor in the atmosphere than those places just because of how it's technically a desert, and then it's so cold that all the water vapor freezes out of the atmosphere. In addition, there's a very stable atmosphere, or stable sky. So it's a very unique location because there's a 6-month-long day followed by a 6-month-long night. So the sun's not coming up on these 24-hour timescales. It's coming up on 6-month timescales, rising and setting. So there's not that, during the winter, there's not that daily rising and setting of the sun to stir up the atmosphere that happens everywhere else. Once it becomes night, it's night for 6 months, and the atmosphere gets really stable. So how do we get there? So it might surprise you to find that we go through New Zealand, actually, where the US Antarctic Center is. And the first leg of the trip involves taking this military flight to McMurdo, which is the southernmost coastal port to access McMurdo. And a lot of where the first explorers landed also to make their journeys to the South Pole, which involves about a 5-hour military flight. And then the South Pole is still another 800 kilometers away, roughly, from McMurdo to roughly the center of the continent. So on a typical trip to the South Pole, you might leave the US about 5 days before you need to arrive at the South Pole. First thing you do is go to this Antarctic Center in New Zealand where they have all these parkas and snow pants, snow boots, all the sort of winter cold weather gear that you might need to survive out there in this minus 100-degree winter cold. From there, in New Zealand, you board this C-17 military cargo jet, which looks like this on the inside. It can seat about 150 people if it's fully packed, haul hundreds of thousands of pounds of cargo. So that's about a 5-hour flight to McMurdo, where you can see McMurdo in the distance here, but it's also the location of where Robert Scott, who was the second person to arrive at the South Pole, or second team, led the second team people to arrive at the South Pole, where his original hut was in 1911. And it might surprise you, but Antarctica is actually a great place to meet celebrities. In my time there, I've actually met like Prince Harry, Prince Albert of Monaco. I've met the Prime Minister of Norway. And then a few years ago when I was down there, John Kerry was down there. And I got to see a talk by him. And he was on my flight down there as well. And you might wonder, why John Kerry actually went, to Antarctica at all. And it's been a lot of speculation on the internet about it. And recently there's been a lot of speculation that he was actually down there to inspect the installation of an energy beam, a weather controlling energy beam, to control the weather in the Pacific. And which he admitted that's what he was there for. So, But I can promise you there's no weather controlling energy beams in Antarctica. But from McMurdo, you often get stuck there a few nights waiting for the weather to clear, the planes to be ready, and you take another smaller, different LC-130 flight, this propeller-based plane on skis, which is, the C-17 has seats. It's pretty spacious. an LC-130 is pretty packed. You're just sitting on cargo netting basically on the sides. It's pretty packed in there. It's loud. But it's a 3-hour flight. It's not that long. And then as you go, you're crossing over the Antarctic mountains, glaciers. You have pretty amazing views the whole way there. And then when you land basically right next to the South Pole. This is what you see when you get off the plane. Here's the station where you live, sleep and live. Can house about 150 people. Carrying all your cold weather gear and luggage back to the station. And then the commute to work, as I said, was about a kilometer walk out to the telescope. Sometimes we take a snowmobile. And then when you get out to the telescope, that South Pole telescope, this is kind of what you see. And then, just to put in perspective how big it is, it's a 10-meter telescope. So it really is this, in this sort of featureless, flat landscape, it stands out as this 70-foot tall structure that really stands out on the continent. So, the SPT was built originally in 2007. This is showing a picture of the original team down there to install it. John Carlstrom is the PI of it, the project at UChicago. I was down there. I've been down there now 11 different seasons working on the project. And it's basically been, SPT has basically been observing for 13 years. This is our 14th winter at the South Pole, basically continuously, where most of our observations are in this sort of South Pole winter when it gets really cold. So the unique thing about the SPT in particular is that it's the biggest diameter, largest diameter telescope of its kind doing these observations. So a big telescope gives you fine angular resolution. The bigger telescope, you can see finer features in the sky. So it has the ability to see signals in this cosmic microwave background, that's light from the Big Bang, the smallest features of any telescope of its kind. And I'll talk a little bit more about this, but one of the things that really drives a lot of these measurements are advances in the detector technology. And so, every 5 years, we have to actually make a lot of these detectors, which are very specialized detectors to make these sort of measurements. And every 5 years ago, the technology is improving so fast that every 5 years, we can actually make a better camera that actually makes better measurements. So we've, from the first camera, we're now on the 3rd generation SPT 3G camera, which I'll talk a little bit more here. So, one thing about these detectors, to make them sensitive enough to see these really faint, 1 part in 100,000 fluctuations or less really now in this light from the Big Bang, we have to cool them to basically about 0.3 degrees above absolute zero, right, to make them sensitive enough. So they're cryogenic. We have to use special cryogenics to get them that cold. And then a state-of-the-art camera roughly 20 years ago only had on order of 16 of these specialized detectors. So today's camera on the SPT 3G has 16,000 detectors. So in roughly 20 years, we've been able to make a camera that's basically 1,000 times more sensitive to do these sorts of observations. And what does a detector look like? So we actually have to use a lot of modern lithography techniques, modern fabrication techniques that you might use to make a microchip, microprocessor, to make these detectors. So this is a picture of one of the detector wafers, which has sort of hundreds of these detectors on it. And if you zoom in on one of these things, this is only about a few millimeters, so it's about 1/8 of an inch diameter, 1/8 of an inch across. So this is actually a little bit like your TV antenna, except we're patterning the TV antenna onto the silicon wafer. This very unique shape, which basically microwave light comes in, excites power on this detector, and then sends that power to these actual little thermometers that surround the detector, which are on the order of 100 microns across, and has a little bit of a superconductor at the center of this thing, which measures the temperature, measures the heat, the input microwave heat onto the device. So with this sort of antenna, you can measure 3 colors. These are at sort of a few millimeter wavelength color, but millimeter wavelength colors. So we measure 3 colors and 2 polarizations to get the different polarization of the light. And we cool this thing to 0.3 degrees, a lot of the above absolute zero. A lot of the development in the project goes to making these sorts of devices. And then SPT 3G has 16,000 of these detectors, which is the largest camera of its kind. So this is the team that went down there a couple of years ago to assemble this new camera. This is usually a lot of the work in the project is just the development and building of this camera. So there's always a big group picture around once we successfully assembled it, and then eventually installed it on the telescope. So one thing I didn't make clear, but you should know, is that the South Pole is actually only accessible about 3 months per year during the South Pole austral summer. So when I'm going down there, usually it's during the summertime, which is our winter because this is the southern hemisphere. So we go in there, if we need to install a new camera, get everything set up, get everything installed, get it working on a telescope, and then we actually leave 2 people behind. There's about 40 people on station to run the whole station for the winter, which started a few weeks ago, technically. The South Pole around February 15th became inaccessible to planes for the next 9 months. So it's going to be so cold that planes can't land there. 40 people are left behind on station, 2 for the project, to take observations during the whole South Pole austral winter. So just to get a sense of what it looks like to take the data, take these measurements, this is sort of showing now how the data looks when we're taking the measurements at the South Pole. One of the things that a great hobby down there for the winter rovers is to take photographs and images, because there's pretty spectacular southern lights down there because you're near the magnetic South Pole as well. So during the nighttime, you also get spectacular astronomical images from the southern lights. So there's one particular. This person in particular, Robert Schwartz. He spent 15 winters at the South Pole. And the good news about that is he's developed his whole scheme and setup to take these long movies at the South Pole and really capture a lot of these observations, photographically, and then also the southern lights. And so here you can see also the Milky Way galaxy kind of coming by through the images, all these lights, colored lights from the southern lights coming up. But so for the most part, when we set up these cameras and take these observations, we set it up to take these measurements during the winter time and then leave the winter rovers down there to basically continuously observe with the telescope for 9 months, where we're basically taking our own version of this long exposure, much like we did with the Hubble Deep Field, but in the microwaves, making these ultra-deep images of this light left over from the Big Bang. So what does it look like? What have we done? So if we go back to this image of this map that we took with this COBE satellite, at the time, this is the first detection of any structure at all in this light from the Big Bang. So fast forward about 21 years, we've now had the Planck satellite, which is a follow-up satellite that had better angular resolution, bigger diameter mirror, more sensitive. And so between the two, you can just see how this structure sort of came into focus. Those blobs that we were seeing before were just due to the limitations of instrumental angular resolution. And now we can sort of see this structure in a much finer detail. So to see what the SBT can do, how our measurements are different, let's just focus in on a small patch of this map, sort of cartoonishly shown here. But so this is what that map would look like if we zoomed in on about 50 square degrees. So this is the moon for scale. This is actual real data from the Planck satellite. I've changed the color scale, but it's contrasts, fluctuations in the distribution in the very early universe. So this is so this is Planck satellite. So this is what our map would look like with the SBT. Well, this is what our map looks like from the SBT from this exact same patch. All right. So, the big thing that stands out immediately is just all these sources popping up, and I didn't want to go that way, and structure. So, as I said before, the unique thing about the SBT is it's the biggest telescope of its kind doing these observations. It's a 10-meter diameter telescope. So it's hard to send a 10-meter diameter telescope into space. So it's about 6 meters or 6 times bigger than the Planck satellite. So that bigger telescope gives you finer angular resolution. So going between the two, all these sort of small bright things, which I'll talk about a little more, sort of pop into focus. It's like sort of putting on a pair of glasses. And then with making our more sensitive detectors and better instrumentation as we go develop that in time, we actually make much deeper maps than we can even do from space, from the ground, just exploiting those advances in detector technology. So let's talk about some of the features in the map a little bit more detail. So you can filter the map and remove some of that large-scale structure so things kind of stand out more clearly. So what are these bright things? So these bright things in the map tend to be black holes in the very massive black holes in distant galaxies that are some of the brightest objects in the sky at these sort of millimeter wavelengths. In addition, some of these other things are actually also distant galaxies, but dust obscured that have these huge amounts of star formation. In addition, you can see these shadows in the map. So these things here. So basically, this light from the Big Bang has traveled across the entire observable universe from 14 billion light years away to get to us. And then along the way, intervening matter can distort that light to some degree. The universe is mostly empty, so for the most part, there's, most of that light comes just straight through. But when you get something that's sort of big enough, massive enough, which we do for these objects called clusters of galaxies, these things that are hundreds of galaxies gravitationally bound together, the biggest ones of those, about 1% of the light gets distorted and creates these faint shadows in the map that we can sort of see these compact objects. So it's a good way to find the most distant objects in the universe because this light has had to travel across the entire observable universe to get to us. In addition, but fundamentally, a lot of this structure that we're seeing, just as a reminder, is really, fluctuations. This isn't just noise in the map. This is sort of variations in the distribution of matter in the very early universe. So it's telling us something really fundamental about the content of the universe at this very early epoch in the history of the universe. So, what have we learned from all this? So, this is an image of the Planck all-sky map. So, you can tell just from looking at the map to some degree that there's sort of, there's a spatial scale to it. It's not just, it might look like noise at some level, but there's actually somewhat of a pattern to it. And encoded in those variations, those fluctuations, the sort of information about the initial conditions of the very early universe, the geometry of the universe, because this light's traveled across the entire observable universe to get to us, and also the content of the universe, what the universe is made of. And when we study this light, we don't just look at these maps. What we really do is we take this thing called an angular power spectrum, and it's much like what you might think of a stereo equalizer for, when you're trying to break music into a spectrum, you can break it into the bass components, the treble components, and you can look at the sound that's coming from different frequency ranges. And very similarly, you can do the same thing with a map or an image to sort of take a spectrum of it to characterize how it looks and how much power is in that map on big scales and small scales. And so the way we do that, this is one of the few plots that I'm going to show, is taking this angular power spectrum. So you can take a spectrum of this map, and what you'll see, and there's prediction was that this map should have a very distinct spectrum with this pattern, and with very distinct harmonics. And you can kind of think of it as sort of overtones. It's sort of equivalent to actually overtones in a musical instrument. These are sort of tones and the scale of the very early universe, where there's sort of scales in the universe that have a preferred size and variation, which creates these harmonics in this spatial spectrum of the map. And it's telling us about the conditions in the very early universe. And so what have our measurements found? And so this is showing a measurement of where the measurements stand today. And the point is that when you combine all the best measurements from the most recent satellites, the South Pole Telescope, we find is there's this very distinct spectrum in that map in terms of the size of those spatial features. And they have these very distinct harmonics, which we've measured with extremely high signal to noise now. And you can tell from that map even, we're really measuring those features with really high signal to noise. And if you try to fit, apply our laws of physics and cosmology to understand this spectrum and relate the laws of physics to it, what we find is that we can actually predict the spectrum very accurately with a relatively simple cosmological model with only a few parameters, except that it favors this universe that has dominated by these two things, dark energy and dark matter, which we don't completely understand. And there are other, and what we're finding in cosmology, even beyond this study of the CMB, is that all our measurements are pointing to that the universe is dominated by these two mysterious components of dark matter and dark energy. And either whether we look at galaxies, clusters of galaxies, structure from more astronomical measurements, or light from the Big Bang, it's all pointing to this very odd universe that's dominated by these dark components. So what do I mean by this? So, the surprising thing that we found is that ordinary matter, what stars and galaxies are made of, what you and me are made of, only makes about 5% of the universe. About 25% of it is this component we call dark matter, which is something that has mass but does not emit or absorb light. So it's effectively, in those simulations I showed earlier, it's basically that some sort of something that has mass that's sort of holding all the structure of the universe together, that's sort of seeding those galaxies and seeding the galaxies that form our universe. But for the most part, we seem to only see it through gravity and how that's seeding that structure. So it doesn't absorb light, it doesn't emit light. And then another mysterious component called dark energy, which dominates the energy density in the universe on cosmological scales, on these biggest scales that we're studying. But it's seemingly causing the expansion of the universe to accelerate. So, surprisingly, you might think, this Big Bang set in motion this expansion, and given time and gravity, that expansion would slowly start getting slowed down from all the just mass kind of pulling on everything else. And it might not completely stop that expansion, but at least would slow it down. But surprisingly, what we found is that the expansion of the universe is accelerating with time. And the only thing that we can, think to explain that is if basically the universe has some sort of energy density space has some sort of energy density to it that's causing basically the universe to get pushed apart. And it's actually something akin to, or could be something equivalent to Einstein's cosmological constant. So even though sort of initially he referred to it as his greatest blunder, it ends up being something that actually could be very prescient in terms of understanding the universe that we see today. And if this you still kind of don't understand what dark matter and dark energy is, that in some ways that's fine. It's really the fact that they have such odd names and vague names that sort of encapsulate our ignorance of them. We can only infer we don't really know what dark matter and dark energy are. We can only infer that their presence there on these big cosmological scales that we're studying. But it sort of indicates that on these sort of universal scales, or physics on the universal scales, we don't really understand something at a very fundamental level. But there's something, mystery to uncover. So in terms of the next steps for a lot of these measurements, this is sort of showing a history of the universe and sort of what we're trying to learn from now on. So, we think the universe began with this Big Bang and underwent this period of this exponential inflation soon after the first fraction of a second, which basically stretched out atomic scale things to universal scales in a very early period. But that's only that part of the Big Bang. Is only a theory. We know the universe started in this hot, dense state, and this has been expanding ever since. Which is the Big Bang. But we don't know the physics behind what put the bang in the Big Bang. Basically, we think it's due to this. There's a theory that is compelling and could explain it, called inflation. But it's that be testing physics at energy scales that are trillions of times above what we could test in the laboratory. So we're trying to use the universe to test this physics. And look for signatures of it left over in this cosmic microwave background, which was emitted, of course, like about 400,000 years after inflation happened. It's very early since in the universe. So that's one big question we're trying to answer. In addition, the CMB is this sort of the universe's sort of perfect backlight, where I've been describing it's traveled for 14 billion years across the entire observable universe to get to us, and we can use that to sort of probe that intervening matter and intervening structure in the universe to actually look for the evolution of dark energy, to try to understand how it's been varying over time, to try to learn about what it is. So as we make better measurements, as we're making better measurements at the South Pole right now, these are two big questions of how did the Big Bang happen, what physics is responsible for it, and then ultimately what is dark energy. All right, so changing topic slightly. So the South Pole Telescope is also part of this network of telescopes called the Event Horizon Telescope collaboration. So in 2017, SPT, so basically I described earlier how a big telescope gives you fine angular resolution. Well, you can create a virtual telescope by combining data from telescopes across the globe, and we've done that with combined the South Pole Telescope with telescopes in Europe, Chile, North America, Hawaii, to create a virtual telescope, basically a telescope the size of the Earth, combining all those data measurements, to basically with the goal of trying to observe the event horizon of a black hole, which is, I'll talk about, is extremely challenging. But with a telescope the size of the Earth, at these wavelengths, these millimeter wavelengths, we're also doing these CMB observations. Turns out you get just enough angular resolution to actually start seeing event horizons in nearby supermassive black holes. So, so what are we trying to do? So, at the center of most massive galaxies, lies a supermassive black hole. So something that's sort of on the order of millions or billion times the mass of the sun, where that sort of has seeded that structure in that galaxy and sort of holding everything together. But as it sort of the universe evolves in time, that galaxy or that black hole at the center of that galaxy is slowly accumulating more and more mass as stars fall in, as matter falls in. And in these massive galaxies, they tend to have these supermassive black holes, greater than 1 million solar masses, that you tend to have some of the most extreme physics in the universe. As that gas is falling in, it's often get heated to extremely hot temperatures where it emits X-rays, gamma rays, and can have phenomena like this sort of jet that you see here, where it's shooting out gas at near the speed of light. So the most massive nearby supermassive black hole is in this galaxy called M87. So at the center here. So this glow that you're seeing is due to the galaxy itself. That is the galaxy, and then at its center is this black hole at the center of this galaxy with this huge thousands of light year across jet getting shot out from the center. So it's the most promising target to actually, in terms of to look for this event horizon using this event horizon telescope. So what do we need to do? So just to put it in context, so this is a picture of the moon, obviously. The moon's about ½ degree across, right? So in terms of how good of angular resolution do we need? So you can break down a degree into 60 arc minutes. 60 in 1 arc minute equals 60 arc seconds. You can break down an arc second to 1,000 milli arc seconds. 1 milli arc second can turn into 1,000 micro arc seconds. So to actually observe the event horizon and this nearby galaxy of M87, you need a resolution of about 40 micro arc seconds, so roughly 100 millionth of a degree. So this black hole is about 50 million light years away, and it's only about the size of our solar system. So it's 50 million light years away, you need actually a really good angular resolution to see this at this sort of 40 microsecond level. And it's sort of equivalent, just to give you a context, it's basically equivalent to seeing a donut on the surface of the moon. You need something, you need to be able to resolve the hole in a donut on the surface of the moon to give you an idea of how good you need to do. So, but earlier this year, we took these measurements in 2017, and earlier this year, the collaboration released this measurement of M87, the event horizon around this M87 at the center of this the supermassive black hole at the center of M87. And of course, made headlines. It was one of the biggest headlines last year. So what are we seeing? So normally light should just, light, traveling through space will just, of course, travel along straight lines in normal space. But even Einstein told us that you put mass in space and it distorts space-time and can bend light. So when you put something really massive like a black hole in space, it can, there's an event horizon within that radius where light can't escape. And then light that's getting really close to the black hole can get bent to extreme angles and really send off light into completely different directions. So, from the 70s even or so, there was a prediction that a black hole should create a shadow due to the event horizon from this extreme bending of light. And so this is a simulation now showing what people, using modern tools today would have predicted for what M87 would look like at different wavelengths, sort of starting in at higher frequencies and then going down to this millimeter wavelength that we're observing. So the unique thing about millimeter wavelengths is it can sort of peer through this obscured cloud of dust and material that's getting infalling into the black hole, and it allows us to see, at the very inner part of the black hole where you're actually able to see some of that infalling material that's potentially falling into the black hole. This is all simulation, right? But almost falling into the black hole, and then seeing that light that's emitting from material behind the black hole, getting bent around it, and then distorted into our direction. So there's this prediction from general relativity that we should see this shadow looking at these wavelengths, and then see this, literally the event horizon, the black part of the black hole, if we find enough resolution at these frequencies. So, and then there's a clear prediction from general relativity as well, Einstein's general relativity, that sort of equates this size of this event horizon to the mass. So this measurement was used by just measuring the diameter of this circle, to actually give us a very accurate measurement of the mass of this black hole, which is about 6 billion times the mass of the sun, 6.5 billion solar masses. But it did agree with what we expected. The mass of this black hole had been estimated using various techniques, but one of them was just to measure this period of nearby stars. There are some stars that are actually in orbit around this black hole, moving at pretty high speed, close proximity. But we can use those. People monitored those stars over decades now to actually get an estimate of the mass of the black hole. And indeed, the measurements from the Event Horizon Telescope agreed with this measurement, but it was actually much more accurate. So, as I was saying, of course, the black hole is gonna cast a shadow on its surroundings, and then by measuring this shadow, we're really testing also gravity at the highest energy scale that we can probe. Look, this is the most extreme regime for gravity that we can actually measure, because you're literally measuring the light that's getting bent around as close as the light can go around the event horizon. So general relativity predicted that this should be pretty close to a perfect circle. And if they were distorted at all, if gravity was not correct, our laws of gravity were not correct, it wouldn't have been quite as perfect a circle as we saw. And to pretty good accuracy, we could still see that was a circle and then measure a mass that was consistent with these other measurements. So it's a test of general relativity at this most extreme scale. So the next step for the project, and we've taken some data already, which might come out later this year, is to observe the black hole at the center of our galaxy. So this is, we talked about, I showed the movie earlier, the Milky Way coming across the sky. So the South Pole is a great place to observe the Milky Way as well. And so if you kind of zoom in on the Milky Way, the Milky Way, the black hole at the center of the Milky Way is only about 15,000 light years away, but it's about 1,000 times less massive than the black hole at the center of M87. So that event horizon is not quite as big physically. It's only, M87 was about a few times the size of the solar system. This is sort of closer to the scale of the Earth's orbit around the moon. But it's, so the event horizon is much smaller physically, but it's much closer. And so similarly with the black hole at the center of our Milky Way, people have done studies of its mass that have been actually much more accurate, many more stars that people have been observing over the past decades to estimate the mass of this black hole at the center of the Milky Way. And with these observations, we're actually able to probe orders of magnitude finer and smaller to actually really probe the physics around the black hole at the center of the Milky Way. So, what are we doing? So, just sort of in summary, there's a lot of big questions left, a lot of research we're still trying to do at the South Pole, trying to understand the physics responsible for the Big Bang and test physics at energy scales much larger that we can measure in the lab at particle accelerator. We're trying to understand these two big mysterious components, dark energy and dark matter, to really understand what they are and how our laws of physics better explain them. And then finally, we're trying to use the South Pole Telescope as part of this network of telescopes to really study nearby black holes, with the next step being really digging in and probing the black hole at the center of our Milky Way galaxy. Okay, thank you very much.
So we're going to have some time for questions. We have a couple people who will be running the microphones, and raise your hand if you're interested.
Over the time that you've been observing on the South Pole, have you noticed any changes either in the general temperature or in the amount of water vapor in the air?
Not really, actually. So the South Pole is at the center of the continent. So the all-time record high at the South Pole is about 7 Fahrenheit. So it sort of typically starts off tens of degrees below freezing already, even at the warmest point. So, and it's hundreds of kilometers inland. So at the coast you can notice it a lot more, in terms of McMurdo, how far in the sea ice goes every year. The sea ice will start becoming clearing out earlier and earlier, but at the South Pole, it's just so far inland and so far, much more uniform landscape that, in terms of climate change or anything like that, you don't really see the effects down there.
I'm constantly wowed by cosmology, but when you showed the M87 and the jet, is that bidirectional or is that unidirectional, indicating that it's really that massive? I'm just talking conservation of momentum here.
Yeah. No. It's sort of It's oh, sorry, I didn't look at the right one. It's I mean, I think it is bidirectional, but it's it's rotated in our direction where, if you can imagine, the black hole or matter spinning around the black hole, it's basically like spinning, pretty close, directed along the line of sight. So we're seeing the jet that's sort of pointing towards us, and there should be another jet behind it, but going the other direction at some level. I mean, I'm sure there's some constraints on it, but the one that just stands out is the one like pointing towards us at some level. So, I mean, I don't know that it has to be on both sides, and it doesn't have to be symmetric by any means, but I'm guessing there's some type of jet, but it's just harder to see because it's going in the other direction.
With the pictures of the CMB through the years, how long did it take to take each of those pictures?
Yeah, so typically when we're doing this, typically on South Pole Telescope, we're replacing the cameras every 5 years. So, to some degree, you can think of it as this, when we're observing this patch of sky, we're basically observing the same patch of sky every 2 days, and then re-observing it every 2 days for 5 years. So you can think of it as like a really long scale integration. And so when we put a new camera on, we start this 5-year cadence of doing this really deep, long exposure effectively. And then after that 5 years, we've built a better camera that's even more sensitive. And it's not like we always observe the same patch of sky. We're usually trying to increase the size of our maps, but then also go much deeper over some certain patch. So it takes, I mean, typically you try to do, observe as long as you can to do as much science as you can until you can actually do that science much faster with better technology. So we try to use that time as well as we can.
The next one's over here on this side.
Hi. Is AI helping you to gather, extrapolate, and look into data at like a much faster pace than you guys have ever been able to do it?
I would say there's a lot of people doing almost research in different types of machine learning or AI in terms of doing different data analysis techniques. But I mean, I would say generally, I mean, right now, I would say a lot of it is more research. I would say a lot of the analysis that we do sort of rely on more traditional methods in terms of, even in this map, you can actually get a lot of the information from more ordinary statistics and don't need to use anything like AI or machine learning or any more advanced techniques. Although I think as the data sets get deeper, and one thing that we're pushing on in the South Pole Telescope data as well is to look for more transients, sort of astronomical phenomena that are varying with time. And so you start sort of digging into the data and trying to do more different types of analyses, looking for more unexpected phenomena. I would say things like machine learning and AI are a little more well-suited to sort of explore that new parameter space. But I would say right now, for the most part, there are people doing a lot of research in those directions, but I would say still a lot of our core analyses don't require machine learning or AI to really get a lot of the information out of it.
Thanks.
Have you been able to measure the distribution or the density of dark matter and dark energy, relate that to the CMB, and if so, how does that relate to our local Milky Way?
Yeah, so well, we've for dark matter, I mean, we've measured the distribution of different objects in across cosmic time to varying degrees. I mean, people have looked at individual galaxies and measured rotational velocities around galaxies, where by measuring the velocity profile of stars moving around a galaxy, you can infer something about the total mass and the distribution of matter in a galaxy itself. You can then do things like that on larger scales. There's clusters of galaxies where those galaxies are moving around these cluster of galaxies are gravitationally bound objects consisting of hundreds of galaxies that have, you can actually measure the distortion of light of background galaxies moving around that cluster to measure the distribution of dark matter in those even larger objects. And then you can even do that on sort of even bigger scales over, thousands of square degrees across big patches of sky where you're looking for lensing distortions to measure even bigger scales, much larger than the scale of cluster galaxies. And to zeroth order, all those measurements and the CMB in addition, and the CMB is actually even measuring the distribution of matter on even larger scales because it's had to travel across the entire observable universe to get to us. So we're measuring light, even matter that's even more distant. And basically all those measurements sort of are consistent with our picture of understanding of dark matter, of this thing that sort of, with time, as time goes on, all those structures are growing because as the dark matter and gravity sort of pulls all that matter together. So, to zeroth order, we can tell dark matter is clumpy because it's just, something that's attracted by gravity. And for dark energy, in terms of its homogeneity and how much it varies over space, I think that's one of actually the active areas of research right now, is to try to see how much it's been changing over time, over the history of the universe, because it's something that's, since, at the time the CMB was emitted, when the universe was much smaller, dark energy contributed a much smaller fraction of the density of the universe. But since it's this parameter that seems to be constant with space, or something that's sort of constant density with space, as the universe has expanded, the fraction of dark energy is, in terms of the amount of dark energy, its contribution to the total energy density seems to have growing with time, effectively, but it's just because the rest of the matter is diluting in a way. But then trying to actually measure how that dark energy has been evolving over that time is actually one of the big topics that we're trying to do a lot of these measurements for. One of the big questions we're trying to answer with a lot of these measurements is, can we see any evolution with dark energy with time? And to zeroth order, right now there's no indication of that, but that's one of the things that we're trying to do, most interested in, trying to put better constraints on to understand what it might be.
First, thank you so much for coming tonight. Great lecture, I appreciate it. My question is, what's the basis for the inference that dark matter does not absorb light?
It comes from a few different avenues. I would say one of the most tangible things that people have done is, I was talking about these clusters of galaxies, for people looking at distortions from lensing of this sort of background galaxies kind of moving through these massive objects and getting distorted from the gravity around these clusters of galaxies. So you can use that method to actually measure the total gravitational mass of a cluster of galaxies and sort of map out where the dark matter is, or where most of the mass of the cluster of galaxies are. But then you also can do things in the optical or X-rays or other wave bands to map out the emission. For a massive cluster of galaxies, most of the emission is actually in X-rays because the gas is so hot in between the cluster galaxies. So you can actually map out the light emitted from those objects from X-rays or optical, and then make a map of the gravitational distortions to map where is the light from those background objects getting deflected. And you can actually see for merging objects that there are two different components, one that sort of, you can see the gas kind of splash into each other and cause shock waves and distortions, but then you see this other gravitational component that sort of has just kind of passed through. So there's, on scales of smaller things, you can tell that those clusters of galaxies are comprised of two different components, one that seems to obey, fluid dynamics and baryonic physics, and another component that just seems to have a gravitational part that doesn't interact. So at that level you can tell, but then also if dark matter had interacted with normal matter in the very early universe, it would actually change that patterns that we're seeing also in the very early universe in the CMB. Those harmonic structure that we'd see would basically change the size of those peaks relative to one another in a way that's predictable from sort of simple physics and that we've tested. So there's a few lines of evidence along those lines of just looking at individual objects, galaxy scale, cluster galaxy scale, to look for interactions between dark matter and the components, and then even on applying those laws of physics to cosmological scales. Everything sort of hangs together that dark matter effectively does not interact with normal matter like we'd expect it would otherwise.
in the middle.
Hi, does quantum fluctuation plays any part in CMB changing, or it has nothing to do with that?
So the quantum fluctuations that I was talking about in inflation, the idea would be just that in the very early universe, when things were extremely hot and dense and compact, if there was this period of inflation, even these small, what I would call quantum fluctuations, that would be fluctuations, on sort of quantum, atomic, subatomic scales, would have gotten stretched out to universal scales very quickly during this period of inflation. So basically those fluctuations would have left their imprint in the distribution of matter in the universe at later times. So, I think basically, and even this, I would say this theory of inflation is trying to connect to some degree this quantum, information on quantum scales onto universal scales, and whether we can construct this theory of physics that basically connects the two. But, to zeroth order, I would say, like shortly after, inflation ended, the quantum information isn't so important, except that, it starts becoming more physics on the scale that we can test in the laboratory in terms of how particles are created in this hot thermal plasma, but not as connected to quantum mechanics, but physics that might be important for particle colliders or something that's a little more routine. I don't know if that answered your question exactly.
Good evening. Good evening.
Go ahead.
Are any of those spots or patches that you see on the CMB growing, shrinking, or shifting?
No, but effectively no. Like that, at some long time scale they would be, but it's something that if you waited something like 100 years, you would basically, with today's technology, you would just start seeing some shifts in the spectrum at a level that would be detectable. But basically on a year-to-year time scale, like it's nothing has changed. The way to think about it is basically that every year that we wait, we can see a year further back into the universe. So on very small scale, at a very small level, we can actually, in principle, see small changes, but it would be, it's happening on such a slow time scale that effectively it's extremely hard for us to measure any differences.
Okay, 2 more questions.
You mentioned at the in the picture with the expansion that this expanded to a universe size that we have now within a very small amount of time.
Yeah.
How is it because the physics, the faster than light type expansion doesn't operate, or the physics that we know now doesn't operate at these very early times in the universe that can go that fast? Thank you.
Yeah. So I think there's a lot of big, there's still a lot of big puzzles in the universe in terms of, one sort of mind bender is just that, as I was saying how the CMB is extremely uniform to 1 part in 100,000 of the same brightness in every direction. But one odd part about that is that if you look in that direction and see light that's taken 14 billion light years, 14 billion years to get to us coming this direction, and then look in the opposite direction, and there's light that's taken 14 billion years to get to us coming from that direction. As far as we know, that we can observe right now, those two sides of the universe are just interacting with one another in terms of that light has literally traveled 14 billion years in opposite directions to get to us. So, but then how is it true that when you look in that direction, that the universe knows to be the same brightness at 1 part in 100,000 level? And so that's a paradox, basically. And so one solution for that is the fact that the universe was causally connected, that those parts of the universe were connected to each other at a very early period and then got ripped apart somehow. And that was sort of motivated this original theory of inflation, that those parts of the universe actually were connected. This period of exponential inflation happened and caused those two things to be shifted to completely opposite sides of the universe, so that they know about being the same temperature today only because they were connected at this very earlier point. But that's actually one of the big questions of, we have ways to explain that. This theory of inflation where space is literally stretched apart due to this physics of inflation would be one potential explanation, but we're trying to ultimately, test that better and sort of come up with predictions based on that model that gives observable consequences that we can actually measure in this light from the Big Bang. And so that's one of the big questions really to try to answer and understand.
Okay. Here, on the left. On the left, Brad.
Yes, thank you for taking my question. Later on, I don't know how many years from now, when Webb telescope eventually goes up, how will that enhance your data?
Well, I would say like one of the things that's actually most interesting for us that's connected to Webb is one of the things, and it's sort of following up a lot of these objects that we're finding. So I described these point sources, these really distant black holes in distant galaxies, and these star-forming galaxies that are really distant, and these shadows. One of the things that from these clusters of galaxies. One of the interesting things about the CMB is that, since it is this backlight that's had to travel across the entire observable universe, across this 14 billion light years of space, so it's actually a really good way to sort of use it to like sort of probe and find the most distant objects, which in principle can, either emit at these frequencies or cause these shadows. So in terms of, my perspective from an astronomer, a lot of these objects are really interesting because you're sort of learning and finding the earliest galaxies and the earliest clusters of galaxies to form in the universe. So, for us, they just look like blobs in the map. We can measure their density and the number of them, and we can learn some things about that actually. But really, from the point of view of an astronomer, you'd want to follow these up with other instruments that can, look at these objects that formed basically in the first billion years of the universe's history, that are some of the first stars, the first galaxies that formed. And so for Webb, the idea is that it's a new space telescope, bigger diameter than Hubble, infrared, to replace the Hubble Space Telescope eventually. But at those infrared wavelengths, it allows you to probe even more and observe even more. Observe these distant galaxies that we're finding and study them in a way that even it's hard for Hubble to do. So I would say like James Webb Space Telescope, when it goes up, will really allow us to study in detail these most distant objects that we're finding in these maps, to really study the chemistry and the astrophysics of these star formation and galaxy formation and these sort of first galaxies that formed in the universe, the first billion years of the universe's history.
All right, let's thank him once more time.